So last time I spent some time to talk about a summary of the resistor, capacitor, and inductor. Yeah, just remember the inductor go with the resistor, okay? Either in serial connection or in parallel connection. But last time I forgot to mention the current divider. Yeah, we are very familiar with the voltage divider. Where is the voltage divider? Here, because the voltage divider is actually the proportion of the length, right? Proportion of the length, and so if you want to get the voltage for the R1, and the proportion is the R1 to the equivalent resistance. Okay, so here is it. You want to get the resistance of the R1, and the numerator is R1. Okay, but for the current divider, it's actually the opposite. Yeah. Okay, and why? Hold on a second. Yeah, why is that? Because the I1 is actually the Vs divided by the R1, right? And what's the R1? What's the Vs? And Vs is equally equivalent resistance times the I, and because they are in a parallel connection, right? So the equivalent resistance is equal to R1 plus R2, and the numerator is R1 times R2, right? Times I. So here's R1, R1. So finally, the R2 is left in the numerator. So that's why. That's why it's opposite to the voltage divider. Okay. If you want to get the current divider for the I1, and there will be the R2 on the numerator. Yeah. For the voltage divider, it's R1. So pay attention to that. Okay. So if you want to get the I2, the current divider of the I2, and you need to put R1 in the numerator. Okay. Yeah. So just remember what you have learned in electrical engineering. And the dot convention, yeah. Because it's easier to put the dot here. The dot here means the connection of the signal. If you want to draw a nice curve like that, it's also okay, yeah. But for me, I like this, yeah. And this symbol is actually used in this textbook. And if you don't put a dot here, and that means no connection, okay? Yeah, so here is a very simple example. We need to calculate the I out and the V out. Okay, yeah, and actually I out is very simple as long as you get, yeah, it's actually the V1 divided by R1, right? Then you can get I out. Yeah, that's easy, but it may be a little bit complicated for the V out because we need to simplify the connection of the resistor here. First, let's take a look. Because R5 and R6 are connected in parallel, so they are easy, right? So this is the equivalent resistance of the R5 and R6 connected in parallel. Yeah, but for the R2, 3, 4, it's a little bit complicated. But first, since R2 and R4 are connected in series, yeah, so we just add them together. We call it R24. R24. Then R24 and R3 are connected in parallel, right? So it's nothing but the R24 connected with R3. in parallel. Okay, so this is the equivalent resistance. Okay, and so after that, since we got R234 and R56, then we can simplify the circuit like this. Okay, no, so this is clear. and again, there's no problem to calculate the IR because IR is simply the V1 divided by R1. Yeah, so it's 10 divided by 1 kilo ohm, so it's 10 milliamp. Okay, so since we need to calculate V out, right? So V out is the voltage division for these two resistors, right? But we need to get I1 I1 minus I2. Yeah, this I1 and I1 minus I2 is the voltage division between these two resistors, right? Yeah. So this is the voltage division. Because we want to get this one. No. We want to get V234. V234. Yeah, we want to get this one. Yeah, and since if we got V234, and how to get V out? V out is actually V1 minus V234, right? Yeah, so we want to get the voltage division of this resistor. Yeah, so we put R234 in the numerator. Okay, and this is the equivalent resistance of R234 and R56. Okay, so V1 and V2 are available. V1 is V1. What's V1? Yeah, V1 is 10, V2 is 20, right? So V1 minus V2 is minus 10, and just put the resistor we just calculated before here. Then we get the V234 is minus 4.23, right? Since we got this, and we need to calculate V out, right? So what's the V out? V out is V1 minus V234. Yeah. But V234 is minus 4, so actually you add it up. So it's 14 plus 2. Okay, so this is easy. It's okay? This is a summary. We talked about this before. But we need to move on to the AC, voltage source and current source, and also the meters. Yeah. And we actually done this before, but I'll just give you a summary first, then you will remember it quickly. Okay, there are four things. We want to learn the current source and voltage source. Also, we need to learn how to measure the current and the voltage. Yeah. But actually, talking about the resistor inside, because we need to have a small voltage drop when we provide the voltage. Okay, so the output impedance in the series should be very small to get a small voltage drop. Okay, and for measuring the current, it's also connected in series, right? Whenever you connect it in series, and the internal impedance should be very small in order to have a very low voltage drop. So those two are the same. Okay, but when you're talking about the current source, because there is a high output impedance in parallel to have a small current draw. Okay, so if you remember when we measure the voltage meter is connected in parallel, right? So again, there is in order to have a small voltage draw, and the impedance is very high. Yeah. So those two are the same. and those two are the same. Yeah, keep those in mind. Then you will follow easier when I talk about the source, two kinds of source and two kinds of the measurement. Okay, so let's go to the beginning. Okay, so when we talk about the ideal voltage source, and what's the ideal voltage source? That means no matter what kind of the current you need, and it will provide a constant voltage, right? So I is equal to V divided by R, and this is fixed. Okay, but the current is variable. It depends on your resistance, right? Sometimes we need to have a high current. So if you need a high current, and then you need to have a low resistance, right? So if you need to supply infinite current, of course it's impossible. But that means you have low resistance. Okay. And I said for this, this is similar to this, yeah, ideal ammeter, because ammeter is connected in series, right? So in order to have a small voltage drop, yeah, then you need to have a near zero input resistance. Okay, so those two are very similar, not the same, but very similar. Okay, and for the ideal current source, because V is equal to IR. And for the current source, the current is fixed. Yeah, but sometimes you need to have a high voltage. Okay, in that case, you need to have a high resistance in order to have a high voltage. So that's why. Yeah. For the ideal current source, it has infinite output resistance in order to supply infinite voltage. Yeah, but of course it's impossible. Yeah, but that means that the resistance is very high. It's about the order of 1 to 10 mega ohm. Okay, so those two are very similar because for the voltmeter, it's connected in parallel, right? In order to have small voltage current draw, and the input resistance is very high. Okay, so those are just the concept. You need to look at the circuit. So this is the ideal voltage source. Okay, because this is a source, so there will be output impedance, and it's connected in series, right? In series, so the output impedance is very small. How small it is? A fraction of an ohm. So actually, you can ignore it. It can be negative. Okay. But the key thing is we all talk about ideal, but when you design your circuit in the board, it's not ideal. Yeah. So it will be a little bit different between the VS and the actual output voltage you get. Okay. So we will show you in the following example. Okay. And this is ideal current source, and there is a output impedance connected in a parallel. Okay, and again, the output impedance is very high in order to have a small voltage, a small current draw. Okay, so how big is it? It's actually uh, about 1 to 10 mega ohm. I think it's over here. Yeah, on the order of 1 to 10 mega ohm. Okay. Yeah, so this is the current source. Okay. And I said ammeter is very similar to the voltage source, right? Because the ammeter is over here, and the current flow into the ammeter. So this is called input impedance. Yeah, it's different from the voltage source. The voltage source providing the voltage, right? So we call this output impedance. Yeah, but for the ammeter, we call this input resistance. And in order to have a small voltage drop, and the impedance is very low, very small, less than 1 ohm. Okay, and this is the voltmeter is because it's connected in parallel. Okay, in order to have a small current drawn, so the input impedance is very high. Okay. Now just remember it. Yeah, we will show you an example. And digital meter, I will show you. I will use a video to show you how to measure it. Yeah, because even though it's very simple, but from my experience, some of you didn't know how to use this basic equipment. So, yeah, and I actually found this video in English because I used some Chinese video before. Yeah, but since this is in my class, yeah, so I changed it to English. But if you don't understand, you can go to some a video from 高工摩克师, then maybe it's easier for you. Okay, so this is an example to show you what's the difference if you have a voltage source, and the voltage source is actually 10. I think it's 10, right? Yeah, Vs is 10. But since there is a output impedance in the voltage source, and also there is an input impedance in the voltmeter. Yeah. So finally, what you get is not 10 volts. Yeah, it will be a little bit different. So this is the purpose of this example. So we have R1 and R2 here, and the equivalent resistance of R1 and R2 connected in parallel is like this. Okay. Then we simplify our circuit to put an equivalent resistance here. Then we need to add the output resistance of the voltage source and the input resistance of the voltmeter. Okay, since those two are connected in parallel, right? So we need to write the equivalent resistance of those two. Okay, so there will be a Req times Z in divided by Req plus Z in. Okay, this is the equivalent resistance. And like I said, when we have a high impedance like this, and actually there is a very small current draw for the VM, so you can actually ignore this. Yeah, just ideally ignore this. When you ignore this, and yeah, sure, let's use this. When you ignore this, and this equivalent resistance is actually connected with ZR in series, right? If you ignore this. Yeah. So that's why it just add ZR into the equivalent resistance here. Okay. So we call it R equivalent prom. Okay. So because we want to get a voltage here, so it's actually a voltage divider for these two resistors. Okay. So the proportion is this equivalent resistance to the overall equivalent resistance. Okay, yeah, but this is very complicated. Yeah, how to check if this is correct or not? Okay, but we know ideally Z in is this. Yeah, the input impedance of the voltmeter is very high. So we say it's infinite. And the output resistance of the voltage source is very low. So we call it 0. So we just use these two terms to check if this is correct. Because ideally, Vm is equal to Vs. What you measure is actually the supply. Okay, ideally. So Req Z in. I'm talking about this term. Okay. REQ plus Z in. So you divide both sides with the Z in. Okay. So it becomes 1 and it becomes Z in. Okay. And because Z in, input impedance of the voltmeter, is infinite. Okay. So you just cross this out, it becomes 0. Okay. So overall it becomes REQ. Okay. Okay. So this is REQ, and this is REQ, and Z out is very small, right? It's 0. So again, it will become 1. The whole term here will become 1. So it's correct. Yeah. After we use this two term to check this formula, and the Vm is actually equal to Vs under ideal case. So it's correct. But actually, in practical, it's not. So we need to calculate. How to calculate? Yeah, you just need to put numbers inside. So in this example, the question told us Zin is not infinite, it's 1 mega ohm. Okay, and ZL is not 0, it's 50 ohm. So you put those in. So REQ plan is actually the whole thing here. Okay, and in the numerator, you just subtract Z out from this term, then you will get this equivalent resistance. Okay, so the numerator is REQ prime minus Z out, right? Yeah, minus Z out. Yeah, so Z out is 50. So you subtract because this is all in the kilo ohm. Yeah, so 50 will need to be translated into 0.5 kilo ohm. Okay, then times the 10 volt, here. Okay, then finally what you got is 9.09 volt. Yeah, it's 1 volt different. Yeah, okay, so it depends on how accurate you need for your circuit. Yeah. So I think the ZR is a little bit too large. Okay, so this just show you a little bit difference between the ideal case and the practical case. Okay. Yeah, just to remind you again, because there is a output impedance connected in series, and in order to have a small voltage drop, and the output impedance is very small, and this is very similar to the ammeter, yeah, because ammeter is connected in the series also, so the input impedance is very small. On the other hand, for the current source, there will be a high output impedance connected in parallel in order to have a small current draw. And this is similar to the voltage meter because voltage meter is connected in parallel. Yeah, so the input impedance is actually very high to have a small current draw. Okay, just keep those in mind. 7. OK， 好，那我用中文 review 一下，不然快睡着了。第一堂课哈，就上礼拜啊，我稍微讲了一下这个 summary 嘛哈，然后这个就是这个电阻、电容、电感哈，在这个串并联的时候，它的这个等效阻抗长怎么样哈？然后 inductor 的话呢，基本上也就是跟 resistor 同样的形式嘛，哦 ，OK， 不管是在串联或是并联这样。那上礼拜呢，就是忘了讲这个 current divider 哈，那 current divider 的话，刚好分子这边哈是刚好相反，如果你要得到 I1 的这个 current 的话，分流的话，那分子的话不是 R1， 它是 R2 这样子。哦，那公式导在这里了哈，这个你们看看就好。那如果说是 current divider 的话呢， 那当然就是很简单嘛，哈，你分子就是看你要得到哪一个那个电阻的分压，好，啊，你分子就放哪一个电阻这样子，好，但是 current divider 刚好是相反的啊，这个是算是 special case 了哈，所以你可以用这个两个这个电阻呢，就可以分别得到分压的分压跟分流这样子 ，OK。好，所以这个蛮重要的，哎，就不用再导，到时候就不用再导这个公式了，直接带就好了哈。然后在这本课本呢，哎，你在画电路的时候，有时候电路很复杂嘛，哈，那电路很复杂的话呢，那通常我们课本就是用这个 dot 代表说有连接这样子，哦，有连接。但如果没有画一个 dot 的话，就代表没有连接，OK。那你也可以如果说你不用这个 dot 的话，那你就要画成这样子嘛，哈。如果说你没有连接，就要用一个这个转弯的，哈。那这个很难画啊，除非你那个软体本来就有这个功能，哦。那以目前来讲，我看大部分都是这样比较多，哦，因为这个比较好画。那课本的话呢，也是用这种的 ，OK。好，再来就是这个简单的 example 了哈。那他要你简化这个东西，然后得到 I out 跟这个V out 哈。那 I out 就很简单嘛，因为 I out 不过是这个 V1 除以这个 R1，好，这个没什么。但重点是要得到这个 V out 哦。那你 V out 看起来就比较复杂，所以我们要先简化一下哦。那简化的话呢，这两个是并联嘛，然后这个呢就还要再处理一下，哦。那 R56是并联嘛，所以就在这里，哦，分子相乘，分母相加 ，OK。那 R234的话呢，因为 R2跟 R4呢是串嘛，对不对？好，串啊，所以这两个就加起来嘛，R2加 R4 嘛，好。但是 R24的话跟 R3是并嘛，对不对？好，所以这个是比较复杂，但就是 R24跟 R3并而已，哦，所以分子的话两个相乘，分母相加，好，然后就可以得到这个 R234跟 R56。那 R234跟 R56得出来之后，你就把它简化成这个电路，哎，这样就清楚了嘛，哈。因为你要得的是 V out 嘛，那 V out 的话呢，那就是 V1 扣掉这个 V234就是 V out 嘛。那怎么样得到 V234？那就是分压，对不对？好，可是它分压分的不是 V1 哦，因为它这里这个 R56这里是接到 V2，所以它是 V1 减 V2 的分压这样子。好，所以这边分压的话是 V1 减 V2 的分压，分压什么呢？上面是 R234，OK。好，那所以 R234跟 R56我们刚刚都算出来嘛，好，都已经算出来。那 V1 V2 的话是什么？哎，又不见了，好像10跟20了哈。啊，对，10跟20哈。OK， 所以这样就可以算出这个 V234啊，V234是负的啦哈，所以 V1 减 V234刚好又把它加回去，所以14.2这样子。OK， 好，这个一定会考哈，因为这很简单，送分题这样子。哦，所以相关的那个练习呢，就是大家要练习一下。好，然后这个比较饶舌一点点哈，所以就讲四种东西啦哈。这4种东西的话呢，就是 voltage source 跟这个 current source 好，然后还有这个 current meter 跟这个 voltage meter 好，就是你要量这个电流跟量电压好的这个仪器这样子哈。那 voltage source 的话呢，它基本上有一个这个输出的阻抗这样子，是串的哦。啊串的话呢，它提供电压，对不对？啊，它如果这个 impedance 很高，那不是白搭嘛，对不对？它就有很大的压降嘛。所以这里的话呢，它的这个输出阻抗就很小。为了什么？为了要有很小的 voltage drop，好，就是压降要很小。OK， 那一样啊，你的 ammeter 也是一样。ammeter 我们现在讲的都是实际的东西哦，不是那个 ideal 的。那实际的东西它都也是有接一个这个电阻嘛，对不对？因为它是串在一起的 ，connected in series， 所以这个电阻的话呢，它也是就也是串在一起的。那为了要有什么这个很小的压降所以它的这个 input impedance 也是很小，所以这个两个就是类似的，隔两号这样子。那相同啊，这两个也是类似的因为这个的话呢，这个 current source 它有一个并联的这个 output impedance， 好，那为了要有，因为它就是要提供那个电流嘛，对不对？啊，为了不要自己浪费很多电流啊，所以它要有一个 high output impedance， 好，那它的这个分流就很小。那这边的话 voltage meter 也是一样，因为它也是并联的 ，OK， 所以这个就是回到我们前面的4个电路，哦。好，那这4个电路的话，一个就是这个 voltage source 嘛，它有一个这个 output impedance 很小，多小？它是在1个欧姆以下，所以就可以把它忽略。那我们说它的歌良好就是这个 M meter 嘛，M meter 对不对？可是 M meter 因为它是量测的，对不对？所以这个是电流输入进去 M meter， 所以这个我们叫做 input impedance， 跟前面这个不一样。前面这个的话 voltage meter 的话，因为它是输出的，所以这个叫 output impedance，OK， 好，所以 M meter 的话，这个电 input impedance 也是很小，可以忽略这样子。那另外一组就是这个current meter， current meter 的话，它有并联，对 current meter， 它有 current source， 讲错了 current source， 它有并联一个 output impedance， 这个 output impedance 就是很高嘛，所以它自己才不会拉太多的电流下去啊，那但它的歌良好就是多高？这个大概是在1到10个的这个 mega ohm， 所以刚刚的那个 example 里面它好像是10的样子，好像是10。好，那因为 voltmeter 的话，它是并的嘛，所以它也是有一个这个input 的 impedance，这个也是很高这样子，所以它的这个那个拉的这个电流才不会太高 ，OK， 好，那这个应该下一节会放一个那个英文版的如何操作3用电表，虽然是很简单，但是因为很多我的经验就很多人都不太会这样子，可能电工实验还没有开始上，可是你在做专题一定要啦，不然这到处碰壁这样子。好，那如果说你觉得这个英文版怎么听都听不懂，而且那个我特别找了一个美国口音的所以他讲的也稍微快一点点，如果你听不懂，可以去找这个高工的模课师，他们都会有录这种很棒的这个影片给高工生去听这样子。好，然后再来的话，这个 example 就是要告诉你说，那如果说不是 ideal 情况之下的话，那你提供一个10伏，这个 voltage source 提供10伏，那这边接收到的会是10伏吗？因为这个是这个什么 voltmeter 嘛，它可能不会是10伏，因为中间可能就是因为什么 output impedance、input impedance 就把它搞了就跟10伏不一样，所以我们要算说它到底是差多少这样子，好，所以这边就是用2个这个 R1 跟 R2 呢来当做例子的那其实它就并在一起而已嘛只不过我们要把这个 output impedance 这个 voltage source output impedance 跟这个voltmeter 的这个 input impedance 要把它放进来，虽然都是跟电压相关的可是它就是一个是串，一个是并 ，OK， 因为这个要压降要小这个是这个这个什么分流要小这样子，好，所以呢放进去之后呢，我们就先把这2个并在一起嘛，对不对？并在一起这样比较简单，所以并在一起就变成是这个样子，可是因为我刚刚说这个，因为它的这个 input impedance 它很高嘛，所以它流到这个 voltage meter 的这个电流就很小这样子。那很小的话，就想说，那你就可以先把它忽略掉，那一忽略掉的话呢，这2个就是串在一起嘛，所以这个就串在一起。好，那串在一起的话呢，我们要得到就是这个的分压嘛，因为我们要量这个的分压就对了。好，那量分压的话呢，就是这个原来的 voltage source 是 Vs 嘛，对不对？那分子的话呢，就是这个电阻嘛，因为它跨在这个电阻上面嘛，对不对？好，那这样的话呢，很复杂嘛，我们要 check 说它到底是对不对 ，ideal 对不对？什么叫 ideal？ideal Vn 当然等于 Vs 嘛，对不对？这个那个什么，那个理想的状态之下，所以理想状态之下的话，那 V in 跟 V out 我们也把它变成理想的，对不对？V out 就是0 ，V out V in 的话就是无穷大。所以我们可以先看一下这个 term， 因为这个 term 最复杂，所以在这里我们先把上下都除以 V in， 对不对？除以 V in 之后呢，上面就变成 Req 嘛，下面的话 Req 除以 Z in， 可是 Z in 的话它是无穷大，Z in 无穷大嘛，所以这一项就变成0，这一项这个是1，对不对？所以呢，分母是1，分子是 Req， 所以它变成 Req，OK，所以这里的话。这一项是 Req 嘛，那这一项也是 Req，Z out 的话是0，所以是 Req 除以 Req 就变成1嘛，所以这个 Vm 就等于 Vs，OK， 这样对啊，代表我没写错所以但实际状况又不是这个样子所以我们要把这个值把它带进去，带什么进去呢？他这边说 Zm 是1个 mega ohm， 刚刚说错，这是一个 mega ohm。但 Z 要不是0它是50，还有点大反正就把它带进去，带到这个 Req prime，Req prime 的话就是这个东西把它带进去，所以分母的话呢，你带进去之后它是 0.550 k ohm 那分子的话呢，就是把，因为它分子就这个东西嘛所以把这个 0.550 k ohm 扣掉这个 0.05这移过去就等于这个东西了那就是分子。所以这样算起来的话呢，它是 9.09，OK， 那 9.09 可不可以？就看你的 application 嘛，有的根本就没关系啊，有的这个 9.09 就真的不行啊，所以就是看你的要求。如果你觉得要更高，那当然这个不太对嘛，50欧就稍微太高一点所以你可以再下降这样 ，OK， 所以这个就是这个 summary。好，我们先下课，大家都快睡。
Hey, how's it going, do-it-yourself first? Today we're going to be going back to the basics and I'm going to be showing you how to properly use a multimeter. And we'll be covering how to measure DC voltage, AC voltage, resistance and continuity, and also how to measure amps. Alright, let's start with DC voltage. Basically the main source of DC voltage in the different devices that we use these days are going to be batteries. Or in other words, anything that uses batteries runs on DC voltage. For example, anything on your car that runs off the car battery, your wireless DeWalt drill, or any camera or camcorder that runs off a battery, they all run off of DC voltage. And if you're wondering, DC stands for direct current. And when you're using the multimeter to measure for DC voltage, you need to set your dial to this setting where you get a V for voltage and the straight and dotted line for direct voltage. And next, you need to make sure your test leads are in the right location. Now, your ground or common test lead is always going to go right here where it says COM. But the red test lead is the one you're going to be switching around based on what you're measuring. And for measuring voltage, you need to place your red test lead here where you see the sign, which is V for voltage. Now, as far as where you exactly want to set this dial when you're measuring voltage, you basically want to set this to the next number up from the maximum amount of voltage you're going to be measuring. So for example, if we're going to be measuring the voltage on this 1.5 volt AA battery, we're going to set our dial to 2 volts on the DC voltage scale. Next, we put our positive test lead on the power or positive side of our circuit, and then the ground test lead on the negative or ground side. And as you can see, we got 1.6 volts, which means this is a fully charged battery. And if you're ever unsure about the amount of voltage you're measuring, you can always start off higher, like we got here on 200, and then come lower to get a more precise reading. Now, if you're ever unsure and hook up your test leads the wrong way, you're going to see this negative sign next to your voltage reading like we got here. Now, this doesn't hurt the multimeter, and it's actually a pretty decent way of finding your positive and negative side of your circuit. Next up, measuring AC voltage. And basically, any device that plugs into your wall socket uses AC voltage. And AC stands for alternating current. And when measuring for AC voltage, your black test lead stays in the same place, obviously, and your red test lead stays in the same place, since again, we're measuring voltage. But you'll need to switch your dial from DC voltage to the AC voltage area, and you know that by this wave sign that next to the V here. So next we're going to see whether we have current at a wall socket or not. And since we get about 110 volts here in the States, we're going to set our dial to 200, which is the next one up from the voltage we're expecting to measure. All right, a word of caution. When measuring high voltage like this, you need to be 100% sure of the integrity of your multimeter, plus the wires that go to your test leads and the test leads themselves. Also, when you go to take your measurement, make sure your fingers are away from the tip of the test lead.
说明一下他在讲的 test lead 写一下，其实这本来是有字幕的不知道为什么我下载之后呢就 是艾伦美模仿嘛，它就只有那个 test lead 就是那个红色跟那个黑色的这个看着 test lead。
But also when you get near the socket, that your test leads don't come into contact or near each other. So next we grab our ground test lead and we're going to put this in the bigger slot on our wall socket. And then we grab our red test lead and we're going to put it on this other side, which is the power side. And as you can see, we got 118 volts coming out of this, which is about right. Also, if you ever wondered what this one is for, this is your case ground. And a good way to check it is to see whether you get a reading when you do this, and we do, so this is good as well. All right, next up, measuring resistance. And resistance is basically the amount of opposition that any substance has to the flow of electric current. So for example, this piece of wood is extremely resistant to the flow of current, whereas this wire has next to no resistance to the flow of electric current. Now, different components of an electric circuit are supposed to have a certain amount of resistance so that the whole system works properly, and that's where knowing how to exactly measure resistance is very crucial. Now, when measuring for resistance, your black test lead stays in the same place, and on this multimeter, the red test lead also stays in the same place because this horseshoe-looking thing is a sign for resistance. And we put our dial here where we get the scale for resistance. And for this example, I'm going to be measuring the resistance for this spark plug wire. And this spark plug wire is supposed to have a resistance of about 10,000 ohms. Ohms being the unit of measurement for resistance. All right, same as before, since we expect a measurement of 10,000, we're going to set our dial to the next number up, which is 20K, or in other words, 20,000 ohms. All right, here we go. And as you can see, we got 9.89 thousand ohms of resistance, or in other words, 9,860 or 870 ohms of resistance for the spark plug wire, which is about spec. All right, next, let's go on to testing for continuity. And testing for continuity basically means checking an electric circuit to see whether current can flow through it. And when testing with a multimeter, your multimeter sends a tiny amount of voltage through that circuit, and then continuity is verified, usually by an alarm or a beep. So for continuity, we set our dial here to this icon that sort of looks like a sound wave. And since we're still in the resistance setting, our test leads stay in the same area. So for example, if you wanted to make sure the wires that go to this connector are in good shape and that electricity or current can travel through them, you would attach one of your test leads to one end, and then your other test leads to the corresponding pin on the connector. And if you hear that beep, that means you got continuity. And if you do this and you don't hear a beep, it means that you got a short somewhere in this wire, or in other words, in our case, maybe a cut or a burnt wire. Now, I did this test on a rather small scale, but this can be done on a much larger scale, or in other words, larger circuits, or even smaller circuits than this, like a motherboard of your computer. A word of caution though, whenever you test for resistance or continuity, you have to make sure that the device is not powered, so either unplug it or remove the batteries. Next up, how to measure amps. Now, when you measure amps on this multimeter, you need to switch your test lead from this slot to one of these. Now, on this multimeter, this first one is fused, which means if you measure more than 200 milliamps, you're going to blow a fuse inside your multimeter, but your multimeter as a whole is going to be saved. But this second one is unfused on this multimeter, which means if you measure more than 20 amps, you're going to ruin your multimeter. Also, if you're unsure about the amount of amps you'll be measuring, but you know if it's less than 20 amps, you can always start with this higher one and then move down for a more precise reading. So for this example, we're going to measure and see how many amps this little light bulb uses. So we put our red test lead in this setting. And next we're going to set our dial, and since this light bulb is battery powered, we're going to set it to 20 amps on the DC voltage setting. And the way you measure amps is basically you place your multimeter on the power side of the circuit you're measuring. So here's the wire from the positive side of this battery. You place your red test lead closer to the power source, and then from there power travels through your multimeter, through the black test lead to the positive side of your device. And next, when we complete the circuit by connecting our ground side, our light bulb turns on and we get our reading, and as you can see, we got 1.95 amps. So it was a great move putting our red test lead on this higher setting to measure 20 amps, otherwise we would have blown a fuse here. And those were the basic functions of a multimeter. Hope that cleared things up. And if you found anything useful in this video, please give it a thumbs up. Also consider checking out some of my other
So if you can understand the conversation here, Congratulations, you have no problem to build a road. Okay, so those are the basic of digital meter, and please check it again in island. Okay, for example, the continuity. Yeah, it's very important to check the solar quality of your circuit. Okay, so let's move on to the Thevenin and Norton equivalent. Again, you have learned this in electrical engineering. Yeah, just to remind you. Okay, the purpose to have the Thevenin and Norton equivalent is in order to simplify your circuit. For example, you have a voltage source and a bunch of resistor networks. That means a complicated resistor network, and you need to simplify, right? So you need to replace these complicated ones with voltage source and a series resistor, and this is the purpose to use a Thevenin equivalent. Okay. And let's move on to this slide. Yeah, we know this is called source transformation from the electrical engineering. So this is like a Thevenin equivalent with a voltage source and a Thevenin equivalent resistor connected in series. Yeah. And this is also equivalent to the voltage source with Thevenin equivalent resistance. The resistance is the same between these two, but it's connected in parallel. Yeah. So this is the whole concept. Yeah. Okay. And for example, we have a bunch of resistor network. It's not complicated though, but this is just an example. Okay. So the voltage is called open circuit. Yeah, because we measure with no any load attached to it, so it's an open circuit voltage, right? And because this is a voltage division for the R1 and R2, and because we want to get the voltage across the R2, right? So we put R2 in the numerator. Okay. And here you just say, in order to get Thevenin resistance, yeah, and you basically short the voltage source. Yeah. After you short it, then R1 and R2 are connected in parallel. So the equivalent resistance is R1 times R2 divided by R1 plus R2. Yeah. But this is a shortcut. So remember, let me explain in a little bit detail. By definition, the short circuit current is equal to Thevenin voltage to Thevenin resistance, right? And this is what we want to find out. Okay, so the Thevenin resistance is equal to actually no. This is not Thevenin. This is open circuit. Open circuit. And open circuit if the open circuit voltage is equal to R2 divided by R1 plus R2 times Vs, right? And short circuit is Vs divided by R1. R1. So after that, you can get Thevenin resistance at R1 plus R2, and the numerator is R1 times R2, right? Yeah. So this is what we learned mathematically in the electrical engineering. Yeah. But the shortcut is if you just show the voltage source, then you can get a series connection, parallel connection of R1 and R2. Yeah. But it's actually from here. Okay. So after you do this calculation, you can replace this resistor network with Thevenin equivalent. Okay. Then it will simplify this black box. Okay. And also you can change this by Norton equivalent. Norton equivalent. And Norton equivalent is you need to have a short circuit current source with the Thevenin resistor connected in parallel. Okay, just remember from the electrical engineering. And I talked about this before. Okay, so let's move on to the alternating current. It's called AC, right? Alternating current. Okay. You all know that for the AC signal, it's not a steady state signal. It's an alternating signal. And we just showed this in sinusoidal form. Okay, and this is a reference. The thin line is the reference, and it's a amplitude of the voltage. The amplitude of the voltage is from the neutral line to the maximum of the amplitude. It's called Bn times sine omega t. What's the omega? Is the angular frequency. And the unit is radian per second. Sorry, I've got to put this. Okay. So the unit is a radian per second. Okay. And so what is the phi here? Phi here is the phase angle relative to the reference. This is the reference. And the phi is actually the deviation here. Yeah. But for this axis, it's a time, right? So how to calculate the phase angle in degree? Then you need to do some calculation because angular frequency, the unit is radians divided by second, right? So you just need to times the time shift, delta t. Then you can get the phase angle. You can get a phase angle phi. Okay. So if you okay, 稍后再试. So if you have a minus a phase angle, that means the signal lags, and that means the signal occurs later in time relative to the reference. Okay, so in this case, the sig line here lags the reference, so it happens behind the reference. So we call this a lag. Okay, phase lag. But in opposite, if the phase angle is positive, and that means it leads the current, and it will start from here. This point will start from here, and it will happen before this reference. Okay, so this is meaning of the sign. Okay. Another important thing is angular frequency. The angular frequency is radians divided by s, right? But normally we view the frequency as in the unit of hertz. Okay, a hertz is nothing but the inverse of the duration. Yeah, but you can actually divide the omega by 2 pi to get the frequency. So omega is 2 pi f is a very important formula to remember. Okay, omega is 2 pi f. So you can convert the angular frequency to the frequency we normally use in hertz. Okay. And another thing is sometimes we need to have a BIOS for your component. Yeah, even though the AC is what we want. For example, for the microphone, for the speaker, you don't need to. You all need to have a AC component. But for microphone, you need to give it a voltage, right? To provide a BIOS. So normally you have a DC offset. So you just basically shift the whole thing up, yeah, to add the DC voltage on top of the AC voltage. Okay. So this is a basic example to calculate the frequency. Okay, using this form. Okay, so if you have a sinusoidal expression as phi times sine t minus 1 volt, and how to get the frequency? Okay, first we get the average voltage. No, this is the mean voltage as 5 volt. Okay, then compare this form omega t plus phi. So since there is a t minus 1, so omega is 1 and minus 1, phi is minus 1. Okay, so you get a 1 radian per second. So in order to calculate the frequency in hertz, so you need to divide the omega by 2 pi. Yeah, so you can get 0.195 hertz. It's very low. So next, we want to get the angular phase angle. Okay, phase angle. It's a minus 1 radian. So how to transfer it to degree? You can simply times 180 divided by pi. Yeah, then you can transfer the radian to the degree. Okay, but since this is the minus sign, so it said the minus sign indicates the signal lag. So it occurs later in time relative to a reference. Okay, and this reference is without the phase shift. Okay. But actually, for the AC signals, not only the sine signal, we also get the cosine signal. And in our electrical engineering, we use this form, right? And you can use Euler's formula to expand this form into cosine and sine. Yeah, but there is the imaginary number here, J, for the sine signal. Yeah, so there will be a phase angle. So what's the phase angle here? The phase angle is actually the angle between the real axis and the VM and the resultant voltage. And this is the phase angle. So you can use arctangent to calculate this phase angle from the VM cosine phi and VM sine phi. Okay. And also we learn some phasor form, phasor form, because even though we write this in the exponential, like Vm exponential j omega t plus phi, right? But this is a little bit complicated, not very complicated. So you can also write this in the phasor form, yeah, Vm times the angle phi, yeah. And I remember we write this Vm phi in the electrical engineering, right? Either one is okay. Yeah. And this is the rectangular form. If you expand this, if you expand this using the Euler's equation, Euler's formula, then you can write this in the rectangular form. And the good thing to use the phasor form is if you multiply two AC signals together, and you simply just add up the phase angle. If you divide one AC signal by another AC signal, and the phase angle will be just a subtraction. Yeah, this is easier to do this in the phasor form. Okay, and where the phase coming from? Yeah, it's because we introduced the capacitor and the inductor. Okay, and if this is Ohm's law, right? If this is the resistor R, right? But if we talk about the impedance, that means the resistance coming from the capacitor and the inductor, and we need to change this term to Z. Okay, so in the electrical domain, Z is equal to voltage divided by I, right? So we need to learn the analogy in another domain. For example, in the mechanical domain, the voltage is analogy to force, and the current is analogy to the velocity. So this is called mechanical impedance. Yeah. And same thing in another domain. For example, I am working on acoustic domain, and the energy side is the pressure. Okay, the velocity side is the velocity times the surface. Yeah, because for example, for a speaker, it's not vibrating like a single mass. It's a vibrating with a surface. Yeah. So there we have a surface area here. Yeah. But just remember the analogy between the electrical side and the mechanical side. Okay. So we need to talk about the concept of the impedance Z coming from the capacitor and the inductor. Okay. For example, you have a inductor. Okay, and you have the I here in the AC form. So it's Im e to the j omega t plus phi. And we know for the capacitor, inductor, sorry, for the inductor, the voltage is the inductance times the derivative of the current with respect to time, right? So since you have the derivative here, so there will be a j omega coming out. Okay, so j omega coming out here, then you need to rewrite this term as L j omega times the I. Because I is equal to Im times exponential to the j omega t plus phi, right? So there will be a j here. Okay, pay attention to this j. And because j is in the because j is in the imaginary axis, right? So the phase angle is 90 degree. 90 degree, yeah. So if you write it in the phasor form, then you can write a 90 degree here. Okay, so this is the inductor. On the other side, for the capacitor, because the voltage is the integral of the current, right? So after you do the integral of the current, and the j omega will be coming to the denominator. Okay, and then you can change this j omega from the denominator to the numerator, becomes minus j. Okay, minus j. And where is the minus j? Minus j is in this direction, right? So it's a minus 90 degree. Minus 90 degree. Okay. So let's try for the capacitor. The impedance can be written as 1 divided by omega c, and the phase angle is minus 90 degree. Okay. So we call this the voltage. The voltage is will lag the current by 90 degrees because since this is a minus sign here, okay. But for this, the voltage will lead the current by 90 degrees because this is a plus sign. Okay, this is just a reverse. But why do we need to calculate this? I will leave this for your exercise. Your exercise, okay. Why do we need this? Yeah. Because, let me see, where is it? Huh? I miss it. Oh, here. If you want to calculate the power, okay, and the power will be the multiplication between the V and the I, right? And there will be a phase angle here, theta, and the theta is the difference between the voltage and current phase. So it's a 5V subtraction, 5V minus 5I. Okay, so this is the phase angle of the complex impedance. Okay, so this is the whole concept. Why we need to calculate the phase angle of the current of the current and the voltage, because we need to get the complicated impedance phase angle. Okay. Okay. So next week we will talk about the power, and I just review what we have learned in Chinese a little bit. OK， 那我用中文再稍微再 review 一下哈，就是我们刚刚讲到这个 Thevenin 跟这个 Norton equivalent 哈，那为什么要做这个东西呢？就是说有些电路是很复杂嘛哈，比如说你拿到一个电路，你根本没有它的电路图啊，就算你有电路图，你要把它放到你的这个自己的电路哈，合起来去做分析也很复杂，所以我们通常都把这个东西当成一个黑盒子哈。那黑盒子的话呢，你就要用量测方法来去定义说，那你要怎么简化这个电路嘛，对不对？那我们量测的话，大部分就是电压源跟电阻，或是电流源跟电阻，就这个东西嘛，哈。所以它就是说，这个 Thevenin equivalent 就是要把这个 voltage source 跟这个 resistor network 哈，这个就是黑盒子啊，很复杂的这个电阻的 network 哈，去简化这样子。用什么简化？变成这个 voltage source 跟这个 series connector 哈，就是用一个电阻串联起来这样子，好，用这样来去简化你的这个黑盒子就对了哈。那这里的话呢 ，RTH 当然是要计算嘛哈。那计算的话，它有提到说，假设我们现在这个复杂电路就是这两个东西啊 ，R1 跟 R2 是这个算是这样的去连接哈，但是我们的 load 是接在这个 R2 上面 ，OK。如果你要算这个 Thevenin 的这个电阻的话呢，那你就是按照我们的这个比较快的方法，就是把这个 VS 把它 short 掉这样子哈 ，short 掉这两个并联嘛哈，所以就会变成这个 R1 R2 除以 R1 加 R2 哈，但是其实它里面的 concept 是 I 这个short circuit 的这个 current 呢是这个 open circuit 的这个 voltage 除以这个 Thevenin 的这个电阻嘛，对不对？哦，那这个是我们要求的啊，所以你只要把这两个相除就好了。VOC open circuit 的这个电压呢，刚刚这边有求出来嘛，哈，因为这个就是这个的这个分压，对不对？哦，这个分压，所以它是 R2 除以这个 R1 加 R2 乘以 VS，OK。那如果我们要求这个 short circuit 的这个current 的话，那 short circuit 的 current 的话，这个 R2 就没有用了嘛，对不对？哦，所以这个 VS 除以 R1，OK。所以把这两个把它相除，刚好就得到这个东西，哦，所以跟我们这个简便的方法是一模一样的，R1 R2 除以 R1 加 R2，OK。好，那因为我们都有学过这个 电工学嘛，有学过这个 source transformation 嘛，哈，所以这个 Thevenin 的这个equivalent 跟这个 Norton equivalent 其实是可以互转的这样子，哈。那重点就是这个 R 都是一样，哦，所以这 R 就是我们的 Thevenin equivalent 的这个电阻嘛，对不对？好，那 I 当然可以借由这个open circuit 的电压跟这个 Thevenin 的这个电阻来去求得出来，哦，所以这个 Norton equivalent 就可以变成这个样子，哦，重点是这个是一样的，哦，所以这个只是回忆一下，你的这个电工学的部分，哦，好，然后这个比较重要，因为呢，因为你们在做专利的时候，常常都是 AC 的哈，这个 DC 比较少一点点哈，所以 AC 的话呢，你就要知道说怎么去量测哈，所有的量测就是，这个什么，不只是三用电表量测了哈，那还有就是说你的这个，示波器的量测这样子，哈，示波器的量测，那示波器的量测。如果说，你们老师的实验室没有示波器，这比较少了哈，或者说你们没有进老师的实验室，怎么去拿到示波器？可以跟那个卢宾玄老师的实验室借，因为他们教育部计划买了好几个那种简易型的，就可以跟他们借这样子，就那个不是一个很大机器啊，就是接电脑的，也是蛮方便的 ，OK。好，所以这个 AC 的这个电路呢，不，这个讯号呢，就是有一个这个 VM，这个 VM 就是我们 amplitude 哈，就是我们的，算是从这个中心点一直到它的最高点，这个 amplitude 叫做 VM 哈，这个 M 是什么 ？amplitude 吗？应该是吧，哈 ，amplitude VM 好，然后重点是这个omega 跟 phi 啦，哈 ，omega 是这个 radio angular frequency， 它的单位是这个 radian 除以秒嘛，哈，那我们要能够得到这个phase angle 的话，那我们要怎么求，哈，那因为这个 phase angle 的话，它单位是 degree 嘛，对不对？radian 这边是 radian 哈，所以你只要把这个 radian 除以 s 的这个那个 angular frequency 呢，去乘以它的时间，然后就会得到这个 radian 了。OK， 好，那这个时间从哪里来？从这边看啊，从这边看，所以有的时候你们在看这个什么，讯号的这个 delay 是多少哈，你就要去比较你的 reference 跟你的这个最后 delay 这个讯号的 time difference 是有多少？这个常常用到哦，专题常常用到。OK， 好，那所以你去量到这个 shift 的话，这个很小哦，都是 microsecond 的这个 scale， 所以你就可以去算它的 phase angle 哦。因为 phase angle 我们比较喜欢看的，你如果说这个 time shift 是多少 microsecond， 就不好表示这样子哈。好，所以你把这个 omega 乘以这个 delta t 就可以得到 phase angle。那只不过它正负号怎么看呢？像以这个例子来讲的话，这边是-1嘛，-1的话，那你可以把它变成你的这个 degree 啊，那负的话代表说是这个negative phase indicate signal lag，就是说它是落后的这样子，那相对于这个 reference 它是落后的，所以以这个来讲的话，这个出现的话，它是有这个 phase shift 的嘛，对不对？它是出现在这个 reference 后面，因为这个时间是往这边正的，所以这个的话就是 phase lag，OK。那反过来讲，如果这个出现在从这里开始，那它就是提前嘛，对不对？那它就是 lead the phase lead the reference，就是提前出现这样子 ，OK， 所以这个是它正负号的意义 ，OK。好，然后另外就是说，其实我们在电工学有讲到这个 exponential 这个 form 嘛，对不对？那 exponential 这个 form 的话，可以用尤拉公式把它展开，那就会得到这个一个 j 的这个部分，这个虚部的这个部分然后这个 phi 是什么意思？这 phi 呢，其实只不过是实部跟我们这个 Vm 的这个夹角而已 ，OK。那学这要干什么？因为我们的 AC 呢，你如果说是运用到我们的电感跟电容，其实它就是有这个 phase 就会出现的。那怎么出现呢？像我们的这个电感的话，那电感的话， 因为它电压是这个电流的微分嘛，对不对？那你电流如果说是 AC 的这个 form 的话，你一微分不是有 J omega 出现吗 ？J omega 出现的话，跑到这里来的话，那你的电压以前是，就是以前就是这个 form 而已啦，哈，你不会去管它的这个 phase 啊。可现在有个 phase 出现的话呢，它有个 J omega， 有个 J 哦，那 J 的角度是多少 ？J 的角度的话，看这个 J 是虚部轴嘛，对不对？所以它是90度啊，所以它有一个90度的什么？因为它是正的嘛，所以它是有一个90度的 phase lead 这样子哈。那90度的 phase lead 的话，那我们就会说这个 voltage will lead the current 好，那个对 voltage will lead the current by 90 degree 好，比这个 current 还要领先90度这样子哈。那这个是这个电感，那电容的话呢，刚好反过来，因为它是这个电流的这个积分嘛，一积分的话，这个 J omega 就跑到这个分母来嘛。那分母来的话呢，你当然可以把它移到分子嘛，所以这个在分母的这个 J 移到分子就变成负 J， 哦，是负 J， 所以它这个负 J 的话，这个负 J 在这里嘛，对不对？哦，所以这个是负90度嘛，负的哦，所以负的话跟刚刚就不太一样，刚刚这里是，这个电感的话呢，这个 voltage 会比那个电流还要领先90度，然后那如果说是电容的话，它就是比这个这个 voltage 跟那个电流呢是 behind 90度，哦，是落后90度这样子。这个要干嘛？因为我们在讲这个 impedance 嘛，对不对？好，那 impedance 的话，这个二之期回去要看哦，这是作业，好，回去自己看。然后，因为我们常要算 power 嘛，对不对？好，那 power 的话呢，它就是这个 Vn 乘以这个 In，为什么除以2？这下次再说，因为这个是 RMS root square 所产生的。重点是这个 power 它也有这个那个 phase 啊，对不对？而这个 phase 是什么？这是重点。西塔是这个 voltage 跟 current phase 的差值就对了。好，所以它是 phi v 扣掉 phi i 这样子。OK。所以它是代表什么？这个 phase angle 就是这个 compressed impedance 的 phase angle。OK， 好，这是重点啊，差不多。那今天上到这边，礼拜五应该可以把这个结束，好，然后就有作业，然后第2章的作业请千万要做一下，好，不用交，这考试都从那里考这样子，包括2之期，到时候我会写哦。好，那我们先下课。